Good morning, ladies and gentlemen. I'd just like to mention that I'm pleased to be able to return to China. I've enjoyed the trip very much so far. What I would like to do this morning is talk about one of our research programs in which we've been following a certain premise. This originated from some of the early work that we did related to CO hydrogenation. And the premise is that perhaps we can create a site on a catalyst that has the capability of activating a carbon-oxygen bond. So I'm going to talk about the use of metal support interaction to see if we can alter catalytic behavior. The first evidence that we could do this was in the work related to CO hydrogenation, as I mentioned. We then asked ourselves, could we activate a carbonyl bond in an organic molecule? And if we could do so, could we do it selectively so that we might be able to hydrogenate a carbonyl bond but not hydrogenate a carbon-carbon double bond or an aromatic bond? And so this is the work that I'm going to rather briefly go through this morning. Now I'm going to take this chronologically and rather briefly in the beginning just to show you some of the earlier results. To test our idea in this case, we took a very simple molecule, one of the simplest we could find. We took acetone first to see if we could activate the carbonyl bond and increase the rate of hydrogenation. If we were successful in this, our next step was to take a molecule such as protonaldehyde and try to hydrogenate the carbon-oxygen bond, but not hydrogenate the carbon-carbon double bond. We did this over a family of well-characterized catalysts, characterized by X-ray diffraction, chemisorption, TEM in some cases. We knew the fractions exposed, we knew the particle sizes, and from this information we could calculate turnover frequencies. To summarize the work with acetone in one slide, and I think the most important aspect of that work was to point out the fact that we found that if we put a metal on titanium, and this morning I'm talking only about platinum on different supports, we found that titanium, when pre-treated appropriately, could markedly increase the rate of hydrogenation of acetone. We were working at low temperatures, slightly above room temperature or at room temperature, 1 atmosphere, and all of these are vapor phase reactions. Now, in this particular figure, I'd just like to point out that with our catalyst, we look at acetone hydrogenation on platinum powder, platinum on silica, platinum on alumina, and platinum on titania, but only after a low temperature reduction at 200 degrees centigrade. All of these catalysts had an approximately similar activity. Notice the logarithmic scale here for the turnover frequency in reciprocal seconds. These catalysts were reasonably close to a number of catalyst behavior patterns reported in the literature. However, if we took the platinum and titanium, reduced it at 500 degrees centigrade, the standard Exxon high temperature reduction treatment to get SMSI behavior, we found that the activity per site increased by approximately 2 to 3 orders of magnitude. And we had a very marked enhancement in activity compared to a normal platinum catalyst. Having obtained this indication that we could indeed activate a carbonyl bond, we moved on to a more complicated system. We looked at protonaldehyde hydrogenation as our first test for selective hydrogenation. This is a more complicated system, and I believe one of our speakers yesterday afternoon spoke somewhat about protonaldehyde hydrogenation. We would like to form protyl alcohol, which could be a valuable intermediate in certain processes. It's a complicated network. The first products could either be protyl alcohol or butyraldehyde. The final completely hydrogenated product is butanol. We can also have isomerization of protyl alcohol to butyraldehyde. This is also a conjugated system. where we have double bonds in the alpha-beta positions. The thermodynamically favored product, if you look at the thermodynamics, butyraldehyde is markedly favored. The free energy change is about 17 kilocalories per mole. The free energy change for protyl alcohol is only about 7. So thermodynamically, the system would like to make butyraldehyde. Again, this reaction goes under very mild conditions. It's a vapor phase, in this case, over these platinum catalysts. As with acetone hydrogenation, when we look at protonaldehyde hydrogenation rates over platinum, in this case, we're comparing catalysts at 353 Kelvin. We're working at very high hydrogen to protonaldehyde ratios to minimize deactivation. This is always a problem with some of these types of reactions. We find that when we compare the activity of these catalysts, if we look at the supported platinum, the activity is not markedly different. However, if we look at the absorption sites, as measured either by hydrogen absorption or carbon monoxide absorption, we find again that normal platinum catalysts are very similar. We look at platinum in silica, alumina, and platinum on this low temperature reduced titanium catalyst, which is not in the SMSI state, and we get turnover frequencies that are quite similar. Again, however, if we take this catalyst, reduce at high temperature, induce the SMSI state, we see that per site the activity again goes up quite significantly, as shown here. One curious feature in all of these reactions, it is true for CO hydrogenation, for acetone hydrogenation, and it is also true for protonaldehyde hydrogenation. We obtain higher rates per site, but it is not due to a lower activation energy. This is one example. If we look at the activation energies on a typical platinum catalyst, it's typically around 4 kilocalories per mole. This is not diffusion limited. These are low activation energies, and they've been established in the literature. However, on the titanium catalyst, the activation energy is twice as high. So, intriguingly, we're getting higher rates, but with higher activation energies. And we have interpreted this to mean that we are creating a new type of active site on the catalyst, and that the increase in rate, which has to be in the pre-exponential, is most likely associated with an increase in the number of sites that are responsible for this reaction. What success did we have in obtaining protonaldehyde? Let's look at these catalysts and look at the selectivity to protonaldehyde. And this will be a little bit hard to see on this view graph. Keep in mind, our desired product is in red, protonaldehyde. Butanol is in blue, the final product. Consistent with the literature, platinum is known to give essentially 100% butyraldehyde. And indeed we found that. Platinum and alumina, platinum and silica, the only product that we observed was butyraldehyde. If we put the platinum on the titanium, even after a low temperature reduction at 200 degrees centigrade, we began to see the formation of some protyl alcohol. And in some cases, of course, we were also forming butanol. The question is now, if we give the platinum the high temperature reduction state, could we enhance the selectivity to butyraldehyde? The answer turned out to be yes. And in this particular case, we were looking at 4 different platinum titanium catalysts. We have not optimized the system. We were comparing the pretreatment effect, the low temperature reduction versus the high temperature reduction. In all of these catalysts, essentially, we saw some protyl alcohol formation. But with our best catalyst, the catalyst shown here, our product distribution under these conditions was 37% protyl alcohol, the balance being butyraldehyde. So in this particular catalyst system, we have increased the activity from protyl alcohol formation from something we could not measure the rates were so low we could not measure, to a rate that is within a factor of 2 of that for the butyraldehyde formation. Consequently, we have increased the rate of proto alcohol formation by at least 3 orders of magnitude, perhaps even more. But the intriguing thing is, we now have a relatively a catalyst that is giving us a reasonably high selectivity for the desired product of proto alcohol. How might we explain this? I'll give you one diagram in this case that we feel applies to all the systems we have studied. It's similar for CO, acetone, and in this case with protonaldehyde. We believe what is happening in these platinum catalysts, particularly after the high temperature reduction, conditions where we know that titania can migrate over the platinum surface, we are creating a large interface between the platinum surface and the titanium oxide. It is very possibly a partially reduced oxide in which we have removed some oxygen from the lattice. If this is done, we could have titanium 3+ cations, perhaps even titanium 2+ cations. Our model at this point is that we have these defect sites at the interface, perhaps an oxygen vacancy, perhaps an open titanium cation, but this acts in a sense to polarize the oxygen end of the bond. By the polarization effect, which is very similar to a solvent effect in homogeneous systems, we feel that we activate the CO bond, and that these are new types of sites that are created at the interface between the platinum and the titanium oxide. Consequently, this bond is activated. The hydrogen that is activated on the platinum surface can then readily and favorably hydrogenate this bond to enhance the selectivity to the alcohol formation. Now, the last system that I wanted to report on is the most recent one that we've studied. And we keep moving toward more and more complicated systems. Also, we get closer and closer to organic chemistry, which is always a challenge for a chemical engineer. But one can see, in this case, that if we talk about acetophenone hydrogenation, even with a simplified system, we have a number of different products that are possible to obtain. The first hydrogenation step can give us perhaps the desired product. In this case, it's phenylethanol. So we're selectively hydrogenating this bond to form the alcohol, and we are not hydrogenating the aromatic bond. Alternatively, we can hydrogenate the aromatic bond, but not the carbonyl bond. In this case, we would form acetyl cyclohexane. Now, these species then can hydrogenate further. In this case, we would form the cyclohexyl ethanol, or with this molecule, we could also form ethylbenzene. And then finally, we could have the completely hydrogenated product here, the ethyl cyclohexane. So our system is more complicated. The selectivity pattern is more challenging, but let's focus on these intermediate products, in particular the phenylethanol. Now, using platinum to test our idea is probably not the best catalyst system. Platinum is known in itself, normal platinum catalysts are known to give a reasonably high selectivity to phenylethanol. Indeed, again, when we went to our reactor system, conducted a vapor phase reaction, looking at acetophenone hydrogenation under rather mild conditions, about 100 degrees centigrade, we found in this case, as reported by others, if we take platinum on silicon or platinum on alumina, we get reasonably high selectivities to the phenylethanol. As the conversion increases, the selectivity drops off, and in high conversions it can drop off rather markedly. The second most significant product here is the other intermediate, where we hydrogenate the aromatic bond, but we do not hydrogenate the carbon-oxygen bond, and in this case, as I mentioned, we form the acetyl cyclohexane. And there are other concentrations of other products. In this case, we see that we have ethylbenzene, and we have the cyclohexyl ethanol in some proportion. If we put platinum on titanium, in this case, reduce it at low temperature, where we might anticipate the behavior is perhaps intermediate between a normal platinum catalyst and a high temperature reduced sample, we find even at low conversions, or even at low temperature, we have enhanced the selectivity to the phenyl ethanol. At low conversions, we start out above 90%. As the conversion increases, this drops off. We see, again, the presence of other products in the mixture. But the important point here is that we have a significant enhancement in the selectivity to the alcoholic species. If we take that same platinum catalyst and reduce it at high temperature, at 500 degrees centigrade, again run vapor phase reaction under our conditions, we find now that we have, again, a high selectivity to the phenyl ethanol. It's above 90%, but in this case we have found that it is less sensitive to conversion levels. In this case we have gone to conversions well above 20%, and we're still about 90% selectivity selective to the phenyl ethanol. Again, we have small amounts of one or two other products here. In other runs, we have taken this even up to 40 and 50% and maintained conversions between 85 and 90% to phenyl ethanol. So we achieve in this case a high selectivity to phenyl ethanol, which is maintained with the titanium catalyst, particularly this one, at high conversion levels. It was interesting in this case when we looked at platinum on silica alumina. This is 13% alumina. It's a very acidic material. Under our general standard conditions in this case, we found at first what appeared to be a quite unusual product selectivity. We found in this case that we got between 90 and 95% ethylbenzene. We repeated this. It indeed was ethylbenzene. We formed only a very small amount of the acetylcyclohexane. And when we started thinking about this and looking in the literature, we found that, particularly in our organic chemistry book, it was not so surprising that we achieved this product, because most likely what we do is hydrogenate this to get the phenyl ethanol. Once we have the phenyl ethanol, this can dehydrate on the acid sites on the silica alumina support. The dehydration step gives us styrene. The styrene then migrates to the platinum, and it's hydrogenated then to give us ethylbenzene. So in retrospect, with a very acidic support like this, we were able to convince ourselves that this selectivity was indeed not too unusual. To summarize what I've just shown you, if we take the selectivities at 20% conversion among these different catalysts, I just want to emphasize some of the improvements that we can achieve. If we're looking for the formation of phenyl ethanol, with their platinum titanium catalyst at 20% conversion, we can achieve selectivities of 90%. These are noticeably higher than those that we obtained with what we would call normal platinum catalyst. With our acidic support, we get a very high selectivity to ethylbenzene. And then, of course, we do have small components of the other possible products in this case that I won't go into right now. Again, we have not optimized these systems. These are just the first catalysts that we made, and then we just used our standard reduction conditions. So, in that, let me just summarize very quickly here and point out the most important aspect here. The point here being that, again, for the high temperature reduced catalyst, we get a much higher activity per absorption site. The other catalysts are somewhat similar. This is lower because we have deactivation problems. But again, on a per site basis, we see this marked enhancement for hydrogenation of the carbon-oxygen bond. I'd just like to conclude then and summarize and say that I think that we have found with these catalysts that metal support interactions can be used to activate carbonyl bonds. We've certainly shown that it can improve the performance of platinum. We've showed a 100-fold enhancement in turnover frequency for methanation, a 500-fold enhancement for acetone, a very marked enhancement in selectivity toward proto alcohol formation. We've been able to increase the selectivity to phenylethanol from perhaps 60% to up to 90% with our supportive platinum catalyst. I mentioned that these higher rates are due not to a lower activation energy, but due to an increase in the pre-exponential factor. We have interpreted that to the formation of new active sites that have this capability of activating the carbonyl bond. I'd just like to mention the co-workers who did all the work in the study: Fred True, Sudhakar, Vishwajit Sen, and Sean Lin and Diane Sanders. Thank you very much.
Basically, I feel a lot of the arguments to evaluate the hydrogen capabilities on the SMI or the non-SMI metal catalyst in terms of the turnover frequency. Turnover frequency is to evaluate the activity after the counting of the active sites under the reaction conditions. It might be better, but generally we use all the CO or the hydrogen absorption to count the active sites, which is very much different from the working condition of the particular processes. So my question is the active sites is involving in the dissociation of hydrogen, and hydrogen is also having the nature of hydrogen or the atomic hydrogen, and also is the allostatic molecules attached on the same active site or the never another site. So we have a lot of the different situations for the discussion of the counting active sites.
Yes, the first thing I'd like to point out that an absorption site is not necessarily an active site. Okay, we use hydrogen chemabsorption or CO chemabsorption, particularly hydrogen chemabsorption, to determine the hydrogen absorption capability. And I do not say that that is an active site, but it basically is a measure of the hydrogen chemabsorption capacity, which may indicate the number of platinum atoms. We don't know what the precise active site is. We do like everyone else. You normalize to the absorption capacity. The second important point here that I'd like to make, we use hydrogen chemabsorption to measure the absorption sites. This is done at room temperature. And if you notice here, almost all of our reactions are very close to room temperature. So now we have, I think, a very good measurement capability of absorption capacity at the temperature and at the reaction conditions where we're conducting the reaction. So I think this might be an even better measurement than some of the high temperature reactions that have been used in the past. The last thing I'll say is, of course, activity per site is a little bit misleading because SMSI reduces the hydrogen chemabsorption. And so the bottom line at some point is you have to look at the activity per gram of catalyst if you want to view it in a commercial sense.
I'd like to ask a question. You introduced a distinction a long time ago in the CO calculation that there is a difference when you talk about COF and activity per unit weight of catalyst that's used. And in terms of the unit weight of catalyst, your activity when you use the titanium is actually lower than with the other supports. Now, my question is, it seems to be a more a change that you can make is that instead of using titanium as a support, you will use titanium as a promoter, in which case you won't waste a lot of your platinum sites by the covering of the titanium. Have you tried that?
Well, let me just first say that the first part of what you said isn't really true. That platinum on titania has a higher activity for CO hydrogenation than platinum on any other support, on a weight basis, volume basis, or turnover frequency basis. The same is true for acetone hydrogenation. the activity of a platinum titanium catalyst for acetone hydrogenation is up to 10 times higher per gram than platinum on any other support. So you can indeed achieve higher activities per gram of catalyst using titanium. You do not always pay a penalty. In this particular case, as you mentioned, our activities, I just picked acetophenone hydrogenation. If you look in this case as far as activity, let me go to the, well, anyway, if we, let me just pick a couple here. If we look at activities here per gram of catalyst, you can see here that the platinum or titanium catalyst per gram of catalyst are very competitive with this one, and they're greater than these two catalysts. So you do not necessarily penalize yourself on a gram catalyst basis. It's very dependent, I think, on how you compare the catalyst. But it's a good point that you mentioned, because this has to be examined very carefully to optimize the activity of the catalyst.
So, my point is, can you use, instead of using titanium as a support, you use titanium as a promoter, where there's only very small amounts of titanium, so that you still have an interfacial site, but you do not block a lot of platinum sites.
Well, okay, some people have done that. Some people have actually promoted certain supported materials with titanium species. We have done that with unsupported platinum. We have put titanium on the surface of platinum particles, and you get the same promotional effect. There's an optimum. We feel the activity is at the interface. Therefore, you want to cover, let's say, approximately half the platinum surface, because that should maximize the interfacial region. So there is an optimum. The problem is how to achieve it, because so far we have not been able to do that quantitatively.
Even though back to the previous discussion, what is the hydrogen dissociation regeneration determinants with respect to the manipulation of flow material, the comparison of the basic device, and the rating in the forum scale for comparison of the real activity. Might be, for example, the hydrogen dissociate at the substrate, and which means it might reach the excess of the reaction site. In this case, the difference in the scales might be the comparison for each different catalytic system. Did you estimate the number of
We have not absorbed formaldehyde under these conditions to try to estimate the absorption capacity. We're very close to the condensation temperature, and it's very difficult to do that without achieving capillary condensation. So we have not done that part. We do not believe that hydrogen association is a really trivial step. And there was very nice work a couple of years ago from a group in Japan where they looked at hydrogenation reactions, I think using hydrogen oxide. They looked at hydrogenation reaction very similar to formaldehyde. They were putting in deuterium to look at deuterium exchange simultaneously with the hydrogenation reaction. They found that the deuterium exchange reaction was much more rapid than the hydrogenation. So we're getting very rapid exchange simultaneously with the hydrogenation we were getting. And again, that's support that this is not supposed to have.
One last question. Immediately without the microphone.
I certainly agree that this is a very interesting system, but I think it is more important to study the nature of active sites and also the number of active sites by means of the approach which I initiated some years ago. That is absorption measurements and also isotope measurements. If it is, for instance, zero reaction with respect to one reactant, then if you switch the reactant to the negative, then you can estimate the number of active sites.
I agree 100%. I fundamental work to be done here using isotopic tracer techniques and other types of transient studies to get information about the true active sites. And I suggest that very strongly as a good research area.
Is it time for one more short question? So enthusiastic.
One more question.
One more question. It's very interesting. We are interested in your work. Before we came here, I mean the type of active site. It's not the number of sites that is concerned, but you pin down the functional group, which is to be hydrogenated. You pin down because you pin down the CO carbonyl group in preference to the CC double bond. That's why you succeed. But in this case, if suddenly you actually raise the activation energy for that, because it is stabilized somewhat on the active side by the carbonyl. So in order to hydrogenate it, you need, say, 7 kilocalories per mole instead of 4 kilocalories per mole. So in your case, would be somewhat equivalent to the catalytic antibody, which can promote the transformation of Dior-Ardern reaction, which is a very strange Dior-Ardern reaction. You increase the frequency, the delta S of that site, so that the increase in activity is due to the increase in delta S, not to the number of sites, but to the orientation of the site to be hydrogenated on the active site, lining up at the right position so that the hydrogen can react on it, whereas the double bond protrudes outward. It is beyond the reach of the hydrogen on the surface. Will that be the, I think, the idea of that?
Yeah, you could be right, but remember, to do that, you need the interface. You need the titanium sites at the interface with the platinum. They have to be next to each other to accomplish that sort of bonding.
Yeah, just a short comment.
All right.
I would like to congratulate Professor Vannice for because it throws off the peripheral side model as proposed by Professor Chikawa in Japan, Professor Sato in the United States. We did similar work with the iron titanium system. We did evaporate titanium into single crystal iron, then measure the bigger frequencies sub CO. We observed a range of frequencies, range of active CO species. We came to the conclusion that the creation of new sites around the periphery of the titanium particles. So this appears to be a partial phenomenon of a system of titanium.
Thank you.
I also like to ask one short question. You mentioned you have turned all of the frequency based on the chemistry of hydrogen on the metal particles, right? And then in this case, there was a point interaction based on the kinetic effects and the